Okay, so the first thing what we did was we, of course, purchased a lot of hardware. Magellan was basically unusual cloud configuration. So if you look at Google and Amazon, most of them have a very different configuration, whereas we felt that since most of our users were, or actually all of our users were scientific applications, we sort of architected it a little bit closer to more the HPC environment, so these machines all had infinite band. Magellan also was across 2 sites, both Argonne and at NERSC. So we had about, this picture here shows more the NERSC set of things. It's reasonably similar setup there. We had sort of the same hardware underlying on both sides, which sort of helped the evaluation quite a bit. And they had a little different configuration based on some of the needs that the Argonne users were looking at. So we had a range of compute servers. They were IBM iDataplex machines, and we also had some flash storage servers, big memory servers, a lot of archival storage. So it was a little bit different, but the flexibility in the architecture, because we had infinite band and Ethernet, allowed us to play and do a bunch of different performance analysis, which we couldn't have done if it were not for this testbed setup. So I should have probably put this slide up right at the beginning, but I figured after having been in summer school for a few days, you probably already knew what a cloud was. I just put this in here mostly because I'll refer to some of these as we go along. And we have used this definition from NIST mostly in our project as to define what cloud computing was, which is there's some amount of resource pooling, there's some broad network access, and it's a measured service that is provided to the users. And there's rapid elasticity that's being where you have capability to scale in and scale out and pay as you go. It's an on-demand self-service, and this sort of comes from the Amazon model where users can basically go in, use a credit card, and pretty much get a service, whereas a lot of times you have a much more complicated process to get access to an HPC center. So when we first looked at this definition, we sort of said, so a lot of these are provided in most supercomputing centers today. Maybe not as much rapid elasticity, maybe not as much on-demand self-service, but we do have a way of measuring the service that's provided to the users. It's a little bit of a virtual money. It's an accounting that we just use to allocate resources. But it's a measured service, it's broad network access, and it's consolidation. A key factor in cloud computing is the fact that you consolidate a lot of resources and you serve multiple consumers. And if you look at most of the supercomputing centers, that's what they are. They serve multiple consumers, usually from the scientific computing space. Okay, so I sort of divided my talk into sort of 2 parts. One was what's the business model for science, which is what I see cloud computing as in this context. And I talk a little bit more about performance and cost in this context. And then a little bit about science plus clouds, which ends up being for catering to the needs of a data-intensive science, and looking at sort of how we use some of these technologies and some evaluation from using Hadoop and MongoDB specifically, since that's what our focus has been recently. So back in 2009, 2010, we did an initial study, performance study, where we took the NERSC 6 benchmarks. So the NERSC 6 benchmarks is a subset of application benchmarks which are used in the procurement process here at NERSC. So they are very representative of the requirements that come from the NERSC workload. They've gone through a rigorous process of selection of codes and algorithmic methods, and they have a very good coverage of algorithm and science area coverage, and there's pointers online which describe how this process was done. So what we did was we took these benchmarks, and we actually had to scale the input sizes when we started out, because most of the commercial clouds that we were dealing with at that point could not handle the large sizes that we were, the large input sizes that we were dealing with. And I'll get into details of this in just a minute. But essentially, we scaled down those benchmarks to be a much more smaller input size, and ran this on a bunch of different systems. So Carver, which is labeled on this graph here, is the same hardware as Magellan. We have two systems, they just separated, but they're essentially the same hardware and pretty much the same system in terms of how they're configured. So Carver was our representation of Magellan cloud infrastructure. This was just bare metal in this experiment here. And then we ran it on Franklin, which was our supercomputing center, which was our Cray supercomputer, which has been retired since then. Laurentium is a local IT cluster here that a number of our mid-range workloads run in. Mid-range is a sort of a vague term that gets used a lot, but essentially we look at sort of mid-range as being the workloads that have concurrency which falls in sort of somewhere between 64 and 1024, and some people might say 512. So it's not high concurrency, but not very low. So Franklin was Laurentium was one of those machines that is used. And then we used two Amazon systems to do this analysis. And Amazon EC2 is the general cloud computing that's provided by Amazon that most of the internet web technology companies use. And then while we were doing this study, they came out with the Amazon cluster compute instances, which were more targeted at the high performance computing codes. So we did this evaluation, and what you're seeing here on the x-axis are the codes that are represented in the NERSC benchmarks, and what you're seeing on the y-axis is runtime related to Magellan. So this is a runtime related to Magellan bare metal. That's sort of the performance our users are interested in general. So that's what we used as our benchmark. Or a baseline rather. So if you look on this x-axis here, as you move on the x-axis, you're seeing an increase in the amount of communication that the app is doing. So GTC is doing lesser communication relatively than Impact, and Maestro 2, which ran on 256 cores, was doing the most amount of communication. So everything else except Maestro ran on 64 cores, and Maestro, we ran it on 256 cores. And when we started running this, especially on Amazon EC2, it was really difficult to even have 256 cores be available at the same time without reliability issues. Things have probably changed since then, and Amazon CC definitely provides better capabilities for larger high concurrency applications. So what you see here is essentially lower the bar, the better it is, and you see that as you go up in concurrence in amount of communication that the app is performing, the communication overhead tends to dominate your runtime, and the runtime related to Magellan starts increasing.